All right, next up, we're going to go to word problems, AKA using these rice tables that I'm about to teach you. And you really need to master this concept, right? We're going to be doing this for the next 2 to 3 chapters. So if you can't make a rice table and understand how it works, why it works type of thing, this class is going to go very poorly for you. So you really need to be comfortable doing this stuff. And in general, it's just a way to organize your thoughts. Right? Technically, you don't have to do rice tables for these problems, but they get complicated, especially because they're word problems. And so rice tables are a way or a method to kind of solve these problems and organize your thoughts. So let's take a look at an example. So we have the concentration of I2 initially and the concentration of I minus initially equal to 0.001 molar. And then I tell you the concentration of I2 is equal to 6.61 times 10 to the negative 4 molar. And then I give you that the equation is I2 plus I minus is in equilibrium with I3 minus. And then I ask you to find the value of K. Right, so I give you some set of information and then I ask you for another piece of information. The first place you want to start off with these rice tables is just to write rice vertically on the left side. So let's see what all of these things stands for. The R in rice stands for reaction, and this is usually given. So this is just our reaction. In this case, it's I2 plus I minus in equilibrium with I3 minus. The I stands for initial concentration. And so sometimes you might know this, sometimes you might not. Up here, we're given some data. We're given that our reactants, both I2, oh, this should be I minus, my bad, and I minus are equal to 0.001. So we can plug these in here. And then if it's not listed, then you kind of assume that the concentration is initially 0, right? And this makes sense. We're just starting off our reaction. And so this is equal to 0. This C stands for change. And so it stands for change in concentration, right? You're starting off your reaction, and then something's going to change by the time you get to equilibrium. And so this stuff is based on the coefficients and the reaction direction. Right. And so in this case, we're going to go from left to right, right? We're going to turn our reactants into products because right now we don't have any products. And so we're going to label this as minus because it's going away, and then just X, it's a variable. We don't have any number in front of it because in this case, all of our coefficients were 1. But if, for instance, if this was a 2, then you'd have minus 2x, right? But it's not. Then this is also minus X because it's a reactant, so some of it's going to disappear. And then this over here is plus X. And then this E stands for equilibrium. And it's just lines I plus C, right? So you're just going to add them up. So in this case, we have 0.001 minus X. Here we also have 0.001 minus X. And then here we just have X. And then the other piece of information that you want to make sure you write down is your K. What is your value of K, right? In this case, we don't know what the value of K is because that's what we want to find, but we can write a relationship for K, right? We know it's products over reactants taken to their coefficients. So I3 minus over I2, and then plus I, or whoops, not plus, times I minus. Times I minus, right? So we know that we're good for there. And then we're given one more piece of data in our problem, and that it's that the concentration of I2, oops, I should have put at equilibrium. The concentration of I2 at equilibrium is equal to 6.61 times 10 to the negative 4. So we know that piece of data, but the other thing that we also know is that our concentration of I2, which is right here, at equilibrium is also equal to 0.001 minus x. And so we can also write that I2 is equal to that as well. And now we can solve for x. Right? Add x to both sides and then subtract by 6.61 times 10 to the negative 4. And then you can write your x is equal to 3.39 times 10 to the negative 4. Right? And so now we know what x is equal to, but we still don't know what k is equal to. And that's our kind of final destination. We want to find k. But as we wrote up here, we know that k is products over reactants. Right? K is products over reactants. And we know that the concentration of I3 minus at equilibrium is just going to be equal to x. We know the concentration of I2 at equilibrium is just going to be equal to 0.001 minus x. And then we also know that the concentration of I minus is equal to 0.001 minus x. And we know the value of x. And so we can plug in x at each one of these, right? And then solve, right? So then you have to just plug and chug. And you should get a value of 776 as your value of k. So there's one example of a rice problem. In this case, you were given some initial concentrations, and then you were given a concentration of one of the components at equilibrium, and then asked to find k. But there's other examples that we'll go through.